Hello and welcome everyone. I am here to discuss on radiation pollution. This module is under the paper Environmental Health in the subject of Social Medicine and Community Health. This module has been developed by a team and the team members are myself, Dr. Madhutandra Sarkar as content writer, Dr. V.M. Gupta as paper coordinator, and Dr. C.P. Mishra as principal investigator as well as content reviewer. This module has been developed with the intention that after completing this module, the students will be able to define the terms radiation pollution and radioactive pollution. To describe the basics of radiation and its types. Describe various sources and doses of radiation. Understand the health effects of radiation exposure. Understand the detection and measurement of radiation. And last but not the least, explain various prevention and control measures of radiation pollution. Radiation pollution has been a matter of big concern after the discovery of artificial radioactivity, development of nuclear weapons, and installation of nuclear reactors for generating electricity. Radioactive pollution is caused by radiations which are emitted by radioactive decay of unstable heavy atomic nuclei. Living organisms are continuously exposed to a variety of radiations called background radiations. If the level of the radiations increases above a certain limit, it causes harmful effects to living beings. Radiation can be natural, that is solar and cosmic, or man-made, that is nuclear. Nuclear radiations are emitted in the atmosphere through natural sources, for example uranium, and anthropogenic or man-made sources, for example nuclear accidents. Radiations are of two types, that is non-ionizing radiation and ionizing radiation. Exposure to any type of ionizing radiation, that is alpha and beta particles, gamma rays and X-rays, can prove harmful and even lethal. Exposure to ionizing radiations can cause mild to very serious effects on the human health and may even lead to death. Some ill effects continue to pass on to future generations. The number of people being exposed to ionizing radiation has increased tremendously in the last few decades. Radiation has become a major factor causing environmental pollution. The harmful level of radiations emitted by radioactive elements, that is, radioactive pollution, is one of the most dangerous forms of pollution having deadly consequences. The greatest concern about ionizing radiation stems from its potential to cause malignant diseases in people exposed to it and inherited defects in later generations. Our senses cannot detect radiation, making this invisible risk seem even more insidious. Another contributory reason for general heightened sense of concern about radiation may be the lack of reliable and accessible information and the misunderstandings that arise. Low levels of knowledge and awareness among general population about radiation, of the possible extent of its threat to human health and environment, and of radiation protection serves to accentuate public fear and anxiety. What is radiation pollution? How to define it? Radiation pollution can be defined as the increase in the level of the natural background radiations above a certain limit. Radioactive pollution can be defined as the release of radioactive substances or high energy particles into the air, water, or earth as a result of human activity either by accident or by design. The sources of such waste include nuclear weapon testing or detonation, the nuclear fuel cycle including the mining, separation and production of nuclear materials for use in nuclear power plants or nuclear bombs, accidental release of radioactive material from nuclear power plants. Sometimes natural sources of radioactivity such as radon gas emitted from beneath the ground are considered pollutants when they become a threat to human health. Since even a small amount of radiation exposure can have serious and cumulative biological consequences, and since many radioactive wastes remain toxic for centuries, radioactive pollution is a serious environmental concern even though natural sources of radioactivity far exceed artificial ones at present. To understand radiation pollution, one should have a clear idea about the basics of radiation. Radiation is energy that is emitted from a source and travels through space and may be able to penetrate various materials. Radiation travels from its source in the form of energy waves or energized particles. Examples include heat or light from the sun, microwaves from an oven, X-rays from an X-ray tube, and gamma rays from radioactive elements. What are the physical forms of radiation? First is electromagnetic radiation and second is particle radiation. Electromagnetic radiation is pure energy with no weight. This form of radiation is like vibrating or pulsating rays or waves of electrical and magnetic energy. It includes sunlight, X-rays, radar, and radio waves. Second one is particle radiation. Particle radiation is tiny fast moving particles that have both energy and mass. This less familiar form of radiation includes alpha particles, beta particles, and neutrons. What is electromagnetic spectrum? The electromagnetic spectrum is the range of all types of electromagnetic radiation. The types of electromagnetic radiation that make up the electromagnetic spectrum are radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, and gamma rays. These differ only in frequency and wavelength. The electromagnetic spectrum ranges from lowest energy or longest wavelength such as radio waves at the left through intermediate wavelength such as visible light to highest energy or shortest wavelength such as gamma rays at the right. This figure shows electromagnetic spectrum. You can see the energy of the radiation shown on the electromagnetic spectrum above increases from left to right as the frequency rises, whereas the wavelength is decreasing from left to right. Sunshine is a familiar form of radiation. Sunshine is one of the most familiar forms of radiation. It delivers light, heat, and suntans. Sunshine consists of radiation in a range of wavelengths from long wave infrared to shorter wavelength ultraviolet. Beyond ultraviolet are higher energy kinds of radiation, that is ionizing radiation, which are used in medicine and which we all get in low doses from space, from the air, and from the earth and rocks. It can cause damage to matter, particularly living tissue. What are atoms and elements? All matter consists of atoms. Nearly all of an atom's mass is concentrated in the nucleus, which consists of positively charged protons and electrically neutral neutrons. Negatively charged particles called electrons orbit the nucleus. All matter consists of atoms. Nearly all of an atom's mass is concentrated in the nucleus, which consists of positively charged protons and electrically neutral neutrons. Negatively charged particles called electrons orbit the nucleus. You can see a figure of atom in the left side. Since the number of protons is unique to each element, the element together with the mass number specify each nuclide. The nuclides of an element, atoms with the same number of protons but different numbers of neutrons, form isotopes of that element. There may be several isotopes of an element. For example, hydrogen has 3 isotopes. hydrogen 1, that is common hydrogen, hydrogen 2, and hydrogen 3, tritium. What is radioactive decay? Radioactive decay is the emission of energy in the form of ionizing radiation. The ionizing radiation that is emitted can include alpha particles, beta particles, and or gamma rays. Radioactive decay occurs in unbalanced atoms called radionuclides. When it decays, a radionuclide transforms into a different atom, a decay product. Here, a schematic representation of a radioactive decay has been shown. Uranium molecules is undergoing spontaneous decay to produce gamma radiation, alpha radiation, and beta radiation. The atoms keep transforming to new decay products until they reach a stable state and no longer radioactive. The series of decay products created to reach this balance is called the decay chain. Each radionuclide has its own unique decay chain. The decay products within the chain are always radioactive. Only the final stable atom in the chain is not radioactive. Some decay products are a different chain chemical element. Every radionuclide has a specific decay rate, which is measured in terms of half-life. Radioactive half-life is the time required for half of the radioactive atoms present to decay. Some radionuclides have half-lives of mere seconds, but others have half-lives of hundreds or millions of years. What is nuclear fission? Nuclear fission is a process through which the nucleus can split as a result of absorbing an additional neutron in some elements. Such elements are called fissile materials. One particularly notable fissile material is uranium-235. This is the isotope that is used as fuel in commercial nuclear power plants. When a nucleus fissions, it causes three important events that result in the release of energy. Specifically, these events are the release of radiation, release of neutrons, usually 2 or 3, and formation of new nuclei, that is fission products. Fission products are the nuclei, that is fission fragments, formed by the fission of heavy elements plus the nuclide formed by the fission fragments radioactive decay. This is a schematic representation of an induced nuclear fission event. Here you can see that uranium-235 is undergoing nuclear fission after absorbing neutron, and it is fragmented into two fission products and releasing neutron and energy. What are the types of radiations? Radiations can be classified into two types according to the effects it produces on matter. First one is non-ionizing radiations. These are the electromagnetic waves of longer wavelength from near ultraviolet rays to radio waves. These waves have energies enough to excite the atoms and molecules of the medium through which they are moving, causing them to vibrate faster. These do not have enough energy to ionize them, that is, not enough energy to remove electrons. Examples of non-ionizing radiations are radio waves, visible light, and microwaves. Second is ionizing radiations. Ionizing radiation is any electromagnetic or particulate radiation capable of producing ion pairs by interaction with matter. Ionizing radiations are the electromagnetic radiations having high energy, such as short wavelength ultraviolet radiations, X-rays, and gamma rays. Beta and alpha radiations are examples of particulate ionizing radiations. Ionizing radiation can also be produced by devices such as X-ray machines. Ionizing radiation may be produced by unstable atoms. Unstable atoms differ from stable atoms because they have an excess of energy or mass or both. Unstable atoms are said to be radioactive. In order to reach stability, these atoms give off or emit the excess energy or mass. These emissions are called radiation. Ionizing radiation can produce charged particles, that is ions, in matter. Ionizing radiation has so much energy that it can knock electrons out of atoms, a process known as ionization. The energetic rays like alpha, beta and gamma, etc. produced in radioactive decay can cause ionization of atoms and molecules of the medium through which they pass and convert them into charged ions. The unstable nuclei decay spontaneously and emit the radiations. These radiations can affect some other non-radioactive atoms to become radioactive or unstable and give out radioactive radiations. Ionizing radiation can affect the atoms in living things, so it poses a health risk by damaging tissue and DNA in genes. There are different types of ionizing radiations, such as alpha particles, beta particles, gamma rays, and X-rays. This figure depicts types of ionizing radiations. You can see alpha is fast moving helium nucleus which can be stopped by skin or paper. Beta is high energy electron. It can be stopped by aluminium plate. And gamma is high energy photons, can be stopped by dense material. What are the sources of radiation exposure? Natural sources of radiation. Most of our average annual dose comes from natural background radiation sources like the radioactive gases radon and thoron, which are created when other naturally occurring elements undergo radioactive decay, space, that is cosmic radiation, and naturally occurring radioactive minerals from internal, that is in the human body, or terrestrial, that is in the ground sources. Next, background radiation. We all are exposed to a certain level of background radiation. Background radiation is present on the earth at all times. It is naturally and inevitably present in our environment, mostly from natural sources, and a small fraction comes from man-made elements. These figures shows background radiation. You can see among natural sources, radon gas from the ground constitute 42%, cosmic rays 14%, buildings and the ground 18%, and from food and drink 11%, whereas artificial sources constitute 15%, among which medical procedures constitute 14%, nuclear power constitute less than 0.1%, and other sources are approximately 1%. There can be large variations. There can be large variances in natural background radiation levels from place to place, as well as changes in the same location over time. A lot of our natural exposure is due to radon, a gas that sifts from the Earth's crust and is present in the air we breathe. About 11%, that is 40 millirem of our radiation dose comes from naturally occurring radioactive materials in the body. Radioactive potassium-40 and other radioactive materials which occur naturally in air, water and soil are incorporated into the food we eat and then into our body tissues. This table shows radioactivity from potassium-40 in some selected foods per 500 grams. Carrot is having radioactivity of 63 becquerel. Banana is having 65 becquerel. The second table shows some radioactive isotopes in human body, a 70 kg adult. Uranium has radioactivity of 2.3 becquerel. Potassium-40 has radioactivity of 4000 becquerel. Next, man-made sources of radiation. It includes diagnostic and therapeutic medical applications like diagnostic X-rays, nuclear medicine, and radiation therapy. It also includes industrial uses like nuclear gauges, smoke detectors, and some glow-in-the-dark exit signs, and also sterilization. Other man-made sources are nuclear weapon test, nuclear explosions, nuclear reactors, means accidents from nuclear reactors, nuclear wastes, and nuclear material processing. Coming to units for measuring radioactivity and its effects. There are different but interrelated units for measuring radioactivity and its effects. Radioactivity refers to the amount of ionizing radiation released by a material. The units of measurement for radioactivity are the curie in US unit and becquerel in international unit. Exposure describes the amount of radiation traveling through the air. The units for exposure are the Roentgen in US unit and Coulomb per kilogram in international unit. Absorbed dose describes the amount of radiation absorbed by an object or person. The unit for absorbed dose is the radiation absorbed dose or RAT in US unit or the Gray in international unit. 1 Gray is equal to 100 RATs. Dose equivalent or effective dose combines the amount of radiation absorbed and the medical effects of that type of radiation. Units for dose equivalent are the Roentgen equivalent man or REM in US unit or sievert in international unit. 1 sievert is equal to 100 REMs. Biological dose equivalents are commonly measured in 1 by 1000th of a REM, known as millirem or mrem. Coming to radiation doses. A dose is the amount of radiation absorbed by the human body, and it is expressed in 3 ways: absorbed dose, equivalent dose, and effective dose. Absorbed dose is energy imparted by radiation to standard mass of tissue and expressed in Gray. Equivalent dose is absorbed dose weighted for harmfulness of different types of radiation and is expressed in sievert. An effective dose is equivalent dose weighted for susceptibility of different tissues to harm and is expressed in sievert. Absorbed dose. Radiation damage to tissue depends on the absorption of energy from the radiation or on the dose of radiation received, called the absorbed dose. Absorbed dose is expressed in a unit called the Gray. 1 Gray is 1 joule of energy deposited per kg of mass. Equivalent dose. The damage producing potential of a given absorbed dose depends on the type of radiation. An absorbed dose from alpha particles is more harmful than the same dose from beta radiation. To put all ionizing radiation on common ground with regard to potential for causing harm, a radiation-weighted dose called the equivalent dose is introduced. The unit is the sievert. The equivalent dose is equal to the absorbed dose multiplied by a radiation weighting factor. For gamma rays, X-rays and beta particles, the factor is set to 1. For alpha particles, the factor is 20. Effective dose. The risk of harm is not the same for the various tissues in the body. For example, it is lower for the bone surfaces than for the tissues of the breast. These can be taken into account by taking the equivalent dose in each of the major organs and tissues of the body and weighting it by a factor related to the risk of harm for that organ or tissue, called the tissue weighting factor. The sum of the weighted equivalent doses is called the effective dose. The effective dose gives a broad indication of the detriment to health. The unit is the sievert. Next, coming to the health effects of radiation exposure. Biological effects of radiation. Radiation damages cells in two ways: indirect effect and direct effect. DNA may be changed indirectly when it interacts with a free hydroxyl radical produced in the water of the cell by the radiation. And radiation can also ionize DNA molecules directly, leading to chemical change. In either case, the chemical change can cause a harmful biological effect, leading to the development of cancers or inherited genetic defects. Radiation affects our health primarily through breakage of DNA molecules. Three things can happen. The DNA is repaired properly. In this case, the cell is repaired properly and it continues to function normally. Second is the DNA damage is so severe that the cell dies. When the DNA or other critical parts of a cell receive a large dose of radiation, the cell may die or be damaged beyond repair. If this happens to a large number of cells in a tissue or organ, early radiation effects, that is deterministic effects. Their severity varies according to the radiation dose received. They can include burns, cataracts, and in extreme cases, death. And third is the cell incorrectly repairs itself, but it continues to live. In some cases, part of the DNA in the cell may be damaged by radiation and may not properly repair itself. The cell may continue to live and even reproduce itself. However, during that process, errors that have not been repaired in the DNA chain will also be present in the cell descendants and may disrupt these cells' functioning. This type of detrimental effect has a probability that is proportionate to the dose, that is, stochastic effect. The timing of the effects or their severity does not depend on the dose. The structure of the cell can change due to improper repair. This alteration could have no further effect or it could result in effects such as cancer and hereditary effects which show up later in life. Next is radiation health effects. Understanding the type of radiation received, that is alpha, beta, gamma and X-ray, the way a person is exposed, that is external versus internal, and for how long a person is exposed, all are important in estimating health effects. Pregnant women and children are especially sensitive to radiation exposure. Radiation health effects can be classified in several different ways: deterministic and stochastic, or somatic and hereditary, or acute and chronic, or early and late. First, deterministic or certainty effect and stochastic or random effect. Deterministic effect is non-random and has a highly predictable response to radiation. There is a threshold of radiation dose above which the severity of the effect is dose-related. Examples include radiation-induced cataract, acute radiation syndrome, or radiation sickness. Stochastic effect. This refers to random and unpredictable effect usually following chronic exposure to low-dose radiation. Probability of an effect increases with dose. However, there is no dose threshold and severity of the effect is not dose related. Examples include hereditary effects and cancer. Next is somatic effect and hereditary effect. Somatic effects are occurring in the body of the exposed person. Somatic effects are further divided into two groups, that is, deterministic effects and stochastic effects. This includes effects occurring after birth that are attributable to exposure in utero. Hereditary effects are abnormalities that may occur in the future children of exposed individuals and in subsequent generations. Hereditary effects are normally stochastic effects. Next is acute effect and chronic effect. Acute health effects occur when large parts of the body are exposed to a large amount of radiation. The large exposure can occur all at once or from multiple exposures in a short period of time. Acute radiation syndrome or radiation sickness is a serious illness. Chronic effect. Chronic exposure is continuous or intermittent exposure to radiation over a long period of time. There is a delay between the exposure and the observed health effect. Examples can include cancer and potentially harmful genetic changes. Prolonged exposure to even low-level radiation increases the risk of cancer. Next is early effect and late effect. A radiation-induced health effect that occurs within months of the exposure that caused is called early effect. All early effects are deterministic effects. Most but not all deterministic effects are early effects. A radiation-induced health effect that occurs years after the exposure that caused it is called late effect. The most common late effects are stochastic effects such as leukemia and cancer, but some deterministic effects, for example, cataract formation, can also be late effects. This table shows health effects of radiation according to the different levels of exposure. Up to 10 millisievert dose range, no direct evidence of human health effects are found. From 10 to 1000 millisievert dose range, no early effects has been reported. It increases incidence of certain cancers in exposed populations at higher doses. From 1000 to 10,000 millisievert, it causes radiation sickness and there is risk of death and increased incidence of certain cancers in exposed populations. Above 10,000 millisievert, it is always fatal. Next, radiation detection and measurement. There are two basic types of instruments which are used for detection of radiation: particle counting instruments and dose measuring instruments. The particle counting instruments are measuring the number of particles, that is electrons, alphas, protons, neutrons, etc., or photons that give a signal in the detector and give the result in counts per minute (CPM) or counts per second (CPS). Dose measuring instruments are also measuring the number of particles or photons, but the result is given in units of dose or dose rate. Sometimes the same instrument is capable of both types of readings. Particle counting instruments are gas field detectors, which include ionization chamber counters, proportional counters, and Geiger-Müller counters, and also solid and liquid scintillation detectors. Dose measuring instruments include field badges and personal thermoluminescent dosimeters. Internal dosimetry for measuring internal irradiation of personnel is done by measurement of iodine and urine analysis. Radiation detection monitoring instruments are used both for area monitoring and for individual monitoring. The area survey meters or area monitors are ionization chamber counters, proportional counters, Geiger-Müller counters, and scintillation detectors. The personal dosimeters or individual dosimeters are pocket dosimeters, field badges, and personal thermoluminescent dosimeters. Finally, coming to prevention and control of radiation pollution. The measures are preventive measures, protective measures to reduce radiation exposure, protective actions during a radiation emergency, and regulations regarding radiation protection and safety measures. The following preventive measures may be adopted to reduce the effects due to both natural and artificial radiations. Atomic explosion should not be carried out in the atmosphere. Fission reactions should be minimized. The number of nuclear installations should be minimized so as to limit the emission of radiopollutants. Closed cycle coolant system may be employed in nuclear reactors so that no radiation leakage through coolant can take place. Radioactive waste generated by nuclear reactors or from nuclear weapons program must be disposed in a manner that they will do the least harm First, the waste may be stored at some place temporarily to allow for the initial very intense radioactivity to die down by natural decay. Nuclear waste should always be sealed in double-walled tanks so that no leaks may take place. In the second stage, some useful isotopes generated during fission in the reactors may be recycled in reprocessing plants. Finally, a permanent storage space for the waste in geologically stable underground deep mines should be established. It has been suggested that these waste may be stored till the waste are reduced to the same radioactivity level as that of a natural uranium mine. Production and use of radioisotopes should be minimum and only for very essential use because radioisotopes once produced cannot be destroyed by any means except by the passage of time. In nuclear mines, wet drilling may be used and tailings properly sealed and protected for radiation leakage. Industrial waste contaminated with radionuclides should be disposed of carefully in specially built tanks. Working places where radioactive emissions are possible should have high chimneys and good ventilation system. In areas where there is a risk of radon leakage from underground, radon concentration should be monitored and protection measures be installed in buildings and homes. Next, protective measures to reduce radiation exposure. It is very important to understand the radiation protection principles of time, distance, and shielding and use the same to reduce radiation exposure. Time, that is limiting or minimizing the exposure time, distance, that is increased distance from the source, and shielding, that is barriers of lead, concrete, or water. Actions minimize one's exposure to radiation in much the same way as they would to protect a person against overexposure to the sun. This figure depicts radiation protection principles of time, distance, and shielding. You can see first one is time, that is less time spent near source, so less radiation is received. Second one is distance, greater distance from source, so less radiation is received. And third one is shielding. The person is standing behind shielding from source and less radiation is received. Next is protective actions during a radiation emergency. An accident at a nuclear power plant, a nuclear explosion, and a dirty bomb are examples of radiation emergencies. If a radiation emergency, that is a large release of radioactive material into the environment, happens nearby, the advice of emergency response officials should be followed. The protective actions for radiation emergencies are depicted below. Get inside, and stay tuned. That means in case of radiation emergency, one should get inside a building, stay inside, and stay tuned with the latest information. They should use radios and TVs, etc. Next is regulations regarding radiation protection and safety measures. The regulatory bodies lay down norms for protection against radiation and also recommend the dose limits for radiation workers and the general public. The International Commission on Radiological Protection (ICRP) is the international regulatory body. In the United States, the counterpart is the National Council on Radiation Protection and Measurements (NCRP), and in India, it is the Atomic Energy Regulatory Board (AERB) or the Department of Atomic Energy (DAE). ICRP provides recommendations on all aspects of radiation protection. The current radiation protection standards are based on three general principles. First is justification of a practice. No practice shall be adopted unless its introduction produces a net benefit. Second, optimization of radiation protection. All exposures shall be kept as low as reasonably achievable, economic and social factors taken into account. And next, individual dose and risk limitation. The dose equivalent to individuals shall not exceed the limits recommended for the appropriate circumstances by the Commission. The triad of radiation protection actions comprise of time, distance, shielding. Reduction of exposure time, increasing distance from source, and shielding of patients and occupational workers have proven to be of great importance in protecting patients, personnel, and members of the public from the potential risk of radiation. The regulatory bodies have recommended the dose limits for occupational workers and general public as well as pregnant women. This table shows recommended dose limits for occupational workers and general public. AERB recommends 100 millisievert for 5-year period for occupational workers. And for general public, the limit is 1 millisievert per year for 5 years. And the table below shows the recommended dose limit to pregnant women. So to summarize, radiation has always been present and is all around us. Life on Earth has evolved with an ever-present background radiation. Natural background sources of radiation are the radioactive gases radon and thoron, which are created when other naturally occurring elements undergo radioactive decay, space, and naturally occurring radioactive minerals from internal or terrestrial sources. We are all exposed to man-made radiation from sources such as medical diagnosis and treatments and activities involving radioactive material. Radiation has become a major factor causing environmental pollution. Radiation pollution can be defined as the increase in the level of the natural background radiations above a certain limit. Radiation pollution has been a matter of big concern after the discovery of artificial radioactivity, development of nuclear weapons, and installation of nuclear reactors for generating electricity. Radioactive pollution is caused by radiations which are emitted by radioactive decay of unstable heavy atomic nuclei. Exposure to these radiations can cause damage to living cells and environment. There are two forms of radiation, that is, non-ionizing and ionizing. The greatest concern about ionizing radiation stems from its potential to cause malignant diseases in people exposed to it and inherited defects in later generations. Understanding the type of radiation received, that is alpha, beta, gamma in X-ray, the way a person is exposed, that is external versus internal, and for how long a person is exposed, all are important in estimating health effects. Pregnant women and children are especially sensitive to radiation exposure. Radiation health effects can be classified into several different ways: deterministic and stochastic, somatic and hereditary, acute and chronic, and early and late. An average person in very few situations is exposed to uncontrolled sources of radiation above background. It is very important to understand the radiation protection principles of time, distance, and shielding and use the same. Time, distance, and shielding actions minimize one's exposure to radiation in much the same way as they would to protect a person against overexposure to the sun. The protective actions during a radiation emergency involve get inside, that is sheltering in place, stay inside to reduce exposure, and stay tuned with the latest information. The regulatory bodies lay down norms for protection against radiation and also recommend the dose limits for radiation workers and the general public. Thanks for visiting EPD Pathshala and listening to this module.